I'm very pleased to present SketchPipe toward accurate sketch-based network measurement on multi-pipeline switches with splitless sketch placement. And this is a joint work from Zhejiang University, the University of Hong Kong, and Fuzhou University, Minjiang University, Yangzhou University, Peking University, and Nanyang Technical University. Modern high-speed programmable switches, such as Intel Tofino2, achieve high throughput by using multiple compound pipelines in parallel. Each compound pipeline has its own ingress and egress processing logic, and packets are routed through the traffic manager between ingress and egress pipelines. This design is very effective for throughput scaling. However, it also introduces an important architectural constraint. Resources are isolated across compound pipelines. That is, memory and computation in one pipeline cannot be directly shared with another pipeline. At the same time, each compound pipeline also provides internal circulation bandwidth, which is separated from normal packet processing. Sketches are widely used for network measurement. They provide compact summaries of traffic statistics with low memory overhead and constant time packet processing. A typical sketch has 3 steps. First, for each packet, it extracts a flow key and hashes it into one or more counter arrays. Second, it updates the corresponding counters. And third, the sketch uses these counters to detect heavy keys, such as heavy heaters, heavy changers, or flow related to attaches. These properties make sketches very suitable for programmable switches. However, deploying sketches on multiple pipeline switches is not as straightforward as on a single pipeline. The common way to deploy sketches on multiple pipeline switches is what we call array split placement. This idea is simple. Each sketch array is split into identical slices, and each slice is placed on one pipeline. Then each pipeline independently measures the packets that pass through it. After first gallons, this seems natural since each packet can only access resources in the pipeline it visits. We place a slice of each array in every pipeline, but array split placement introduces 2 serious accuracy problems. The first problem is redundant measurement. In array split placement, packets from the same flow may traverse different pipelines. For example, routing rules, ECMP, or per packet load balancing can send packets with the same flow key to different pipelines. As a result, the same flow may be measured repeatedly by multiple slices. If each flow originally needs k counters in a sketch, then in array split placement, it may consume k times n counters, where n is the number of pipelines. This wastes scarce switch memory and increases hash collisions. Eventually, measurement accuracy will drop. The second problem is measurement imbalance. Real network traffic is highly skewed. A small number of flows may contribute a large fraction of packets. Since flows are distributed across pipelines according to routing behavior, some pipelines may become hot while others receive much less traffic. Under array split placement, different slices observe very different workloads. Their counter values become highly unbalanced. When we aggregate these slices to detect heavy keys, the results become inaccurate. And in the experiments, the precision of the array split placement can drop by up to 80%. So the core issue is array split placement matches the hardware, but it breaks the statistical behavior of the sketches. To address this problem, we propose SketchPipe. The key idea is simple. SketchPipe does not split sketch arrays. Each array is placed exclusively on one compound pipeline, and we call this splitless sketch placement. This directly avoids redundant measurements and measurement imbalance. However, splitless placement creates a new overhead challenge. If a packet arrives at a pipeline that does not contain all sketch arrays, how can those remote arrays still observe the packet's flow key? SketchPipe uses asynchronous measurement. Normal packets are processed normally. It only caches their flow keys and then uses synthetic state packets to transfer those cached keys to remote sketch arrays via internal recirculation bandwidth. Okay, let's look at an example. Suppose a packet of flow F1 enters pipeline 1. In SketchPipe, this normal packet is measured by the local sketch array if one exists. Then, before the packet leaves the ingress pipeline, SketchPipe caches its flow key. The cache entry records the flow key, the packet count for that key, and the IDs of the sketch arrays that still need to measure this key. After that, the normal packet is routed to its egress as usual. The important point is there is no inter-pipeline routing for normal packets, and normal packet processing remains almost unchanged. Now, how do remote arrays receive the cache key? SketchPipe generates state packets inside the switch. A state packet retrieves a cached flow key and its packet count, then piggybacks them on its packet header. The state packet is then routed to the pipelines that contain the remaining sketch arrays. When it reaches a target array, it updates the corresponding counters using the cache key and count. After finishing the update, the state packet can be recirculated and reused for the next cache key. This way, SketchPipe gives each sketch array a complete view of flow keys, but it does not force normal packets to visit all pipelines. SketchPipe has 3 inputs: the sketch program, the switch model, and the routing rules. It formulates splitless placement as an optimization problem. The objective is to minimize resource consumption, including the number of occupied compound pipelines and the number of occupied mesh action stages. The constraints ensure that sketch is correctly placed. For example, resource usage must not exceed hardware capacity, and most importantly, each sketch array must be placed on exactly one pipeline. SketchPipe solves this optimization problem and produces both pipeline assignment and stage assignment. The second part is the cache. The challenge is that switch resources are limited. We cannot simply cache every packet. So SketchPipe uses a light-weighted cache based on the key observation that network traffic is skewed. The number of distinct flow keys is much smaller than the number of packets. Therefore, SketchPipe caches per flow information. Each cache entry stores the flow key and the number of packets using this key, and the IDs of arrays that still need to process this key. When multiple packets from the same flow arrive, SketchPipe only increments this count. This preserves measurement semantics because sketch updates for the same key are equivalent to adding the aggregated count. For collision, SketchPipe uses an evict on collision policy, which is simple enough for switch and performs well in practice. The next challenge is how to control the overhead of state packets. SketchPipe uses 2 strategies. First, it allocates dedicated traffic manager buffer space for state packets. This preserves state packets from competing with normal packets for buffer space. And second, state packets are processed using internal recirculation bandwidth. This bandwidth is separate from normal packet processing bandwidth. So state packets do not consume the normal data plane bandwidth. With these 2 mechanisms, SketchPipe can complete asynchronous measurement while preserving normal packet processing performance. We implemented SketchPipe on a 64 by 100 gigabits per second Tofino switch with 2 compound pipeline and a 32 by 400 gigabits per second Tofino2 switch with 4 compound pipelines. The splitless placement component is implemented in C++ with a Groovy solver. The data plane logic is implemented in P4, and the cache uses register arrays. And the state packets are generated using the packet generator in the switch SDE. Our testbed contains 8 servers equipped with 100 gigabits per second NICs. We evaluated SketchPipe with a broad set of sketches. We used both WAN traces and data center traces, including CIDA, MAWI, and IMC traces. We evaluate several monitoring applications, such as heavy hitter detection. We compare SketchPipe with array split placement, patch cache, and an ideal one pipeline placement. The main metric are precision, recall, and F1 score. For measurement accuracy, SketchPipe achieves near ideal accuracy across different sketches and applications. Compared with existing solutions, SketchPipe improves accuracy by up to 81% and reduces measurement errors by up to 2 orders of magnitude. And the key reason is that SketchPipe avoids both redundant measurements and measurement imbalance, while still ensuring that each array reaches a complete view of flow case. For entropy estimation, SketchPipe also significantly reduces errors. Compared with array split placement, SketchPipe achieves up to 2 orders of magnitude lower error. We also evaluate SketchPipe under diverse traffic traces. The result shows that SketchPipe generalizes well across both data center and WAN traffic. This is important because traffic characteristics can vary significantly across environments. Data center traffic can be highly skewed, while WAN traffic may have different flow distributions. And across these traces, SketchPipe constantly achieves the best or near best accuracy. In practice, a switch may need to run multiple monitoring applications at the same time. We therefore evaluate SketchPipe when heavy hitter detection and super spreader detection run simultaneously. The result is that SketchPipe still outperforms baselines by about 30% higher accuracy. This shows that SketchPipe is not only useful for a single sketch or a single application, but can also support multiple measurement tasks under shared switch resources. Next, we stress test SketchPipe under extreme traffic imbalance. Array split placement suffers significantly because some slices receive much higher workloads than others. In contrast, SketchPipe remains robust and retains near ideal accuracy in all tests. This confirms our main motivation. Once sketch arrays are split across imbalanced pipelines, accuracy can degrade sharply. By keeping each array splitless and transferring case asynchronously, SketchPipe avoids this problem. We also study scalability when the number of compound pipelines increases from 8 to 128 in simulation. This is important because future switches are likely to use more pipelines to scale throughput. These results show that SketchPipe retains high accuracy, while array split placement suffers substantial accuracy drops. This suggests that SketchPipe becomes even more important as switch architectures continue to scale out through more pipelines. SketchPipe is resource efficient. It uses at least 20% fewer resources to achieve the same level of accuracy. In our implementation, pipeline resource usage is below 10%, buffer usage is below 1%, and recirculation bandwidth usage is below 0.21%. This result shows that SketchPipe's accuracy gain does not come at the cost of large hardware overhead. We also measure switch performance overhead because normal packets are processed without inter-pipeline routing. SketchPipe introduces only small latency overhead. Okay, to summarize, modern multi-pipeline switches create a new challenge for sketch-based network measurement. Existing array split placement fits this hardware structure, but it causes redundant measurements and measurement imbalance, which significantly reduce accuracy. SketchPipe addresses this problem with splitless placement and asynchronous measurement. And our implementation shows that SketchPipe achieves near ideal accuracy, improves accuracy by up to 81%, and reduces errors by up to 2 orders of magnitude, and introduces only small overhead. Okay, that's all. Thank you for listening, and welcome to email questions to the first author. Thanks.